Okay, welcome to chapter 5, part 4, I think, right? Because we just finished chapter 5, part 3. Okay, I'm finally getting a chance to record this. It's kind of late in the evening, but I wrote to myself, start here. So when I left off, we had just talked about the effect of the lone pairs on the molecular geometry, and we've gone through all the charts. So for right now, I'm talking about the derivatives when you have trigonal bipyramidal. In trigonal bipyramidal, once again, you have a central atom being surrounded by 5 electron groups. So it says here, when there are 5 electron groups around the central atom and some are lone pairs, they will occupy the equatorial positions because there's more room. So once again, starting with the 5 electron groups, the central atom is in the middle. You have the axial position. So let's say the central atom is A, generic element A, surrounded by 2 axial groups, right? And 3 equatorial groups. If you're going to replace one of these groups with a lone pair, what they're saying here is the lone pair should be in the equatorial position because there's more room. Remember, lone pairs need more room to spread out. And for that reason, you're going to have to replace a bond in the equatorial position with a lone pair. Okay? And so, of course, by doing that, your bond angles will be less than 90 and 120. Okay? So we go through the variations here. Once again, it shows you that the lone pairs should be placed in the equatorial region. You see that here. And that's how we're able to get the seesaw configuration of the seesaw shape. It's seesaw, right? And then from here, if you have to remove the second set of lone pairs, once again, go after the bonded group in the equatorial region to replace that with a lone pair. And that's how we get the T-shaped molecular geometry. And once again, the remaining bond angles are now just 90 degrees because 90 on top and 90 on the bottom. So 90 degrees when you have T-shaped. And then finally, when you have to remove the last lone pair electrons, the last lone pair electrons does come from the equatorial position again. And what we are left with now is a bond angle of 180 because you have 2 axial bonds and they are 180 degrees far apart from each other, or 180 degrees apart from each other, right? And so the resulting geometry is going to be linear. With octahedral, when you're trying to place the lone pairs, it doesn't really matter where you place the lone pairs. You have the same orientation or the same organization of the remaining bonds, which will then form square pyramidal. It looks like a pyramid with a square base, right? So it looks like that, square pyramidal. And when you move the second bonded group to get a lone pair, when you're trying to replace the second bonded group with a lone pair, you essentially replace the one on top on the opposite side of the first one. So we end up with square planar that looks like an X, like a plus or an X. I guess this way looks more like an X, right? So I am happy to say we're done with the big chart. All we're going to be doing from here on is just applying this and solving problems, right? So let me go ahead and answer this question right here. We're told we're trying to do a conceptual connection. Suppose that a molecule with 6 electron groups were confined to 2 dimensions and therefore had a hexagonal planar. A molecule with 6 electron groups were confined to 2 dimensions and therefore had a hexagonal planar. So we have a molecule, let's call it A, and it has 6 electron groups, surrounding groups, right? And this molecule is 2D according to the statement here of this text, or it can be called hexagonal planar electron geometry. If 2 of those 6 groups were lone pairs, where would they be located in the figure shown here? Remember that lone pairs, I kind of casually call them introverts. They want to be far from each other as possible because each lone pair is trying to spread out, right? And repel any group it's very close to. And each lone pair is doing that effect to a neighboring lone pair. So if lone pairs had their way, they would rather not be paired with other lone pairs. And so the best way to do it is to place them as far away from each other as possible. If we select 1 and 2, they're adjacent next to each other, right? If we do 1 and 3, it's better than 1 and 2. But 1 and 4 is the most ideal because you can have the lone pairs very far from each other, and therefore they have little influence on each other. Okay. Now for the molecule, what will happen here is the geometry or the shape will be square planar, right? Because you essentially have a lone pair on top, on the bottom, like this, and then the remaining bonds will be square planar. But this is a hypothetical. It's not a real molecule. Okay. Now we're looking at molecular geometry and electron group repulsions. We're told which statement is always true according to Vesper theory. The key term here being always true, right? It can't be kind of true. It has to be true, because it's always true. The shape of a molecule is determined only by repulsions among bonding electron groups. While when we're looking at the shape of the molecule, we focus on the bonding electron groups. Remember, the non-bonding electron groups or the lone pair exert an effect. That is why when we look at water, right? Water has 2 bonded groups and 2 lone pair groups. This is not linear. So remember, it's not linear because the lone pairs exert an effect. The lone pairs end up on the same side of the molecule, and they bend the remaining bonds, making it bent. It's not linear, but bent. So we cannot just ignore the effect of the lone pair, right? Because the lone pair and it's the repulsion is what gives us the different shapes, okay? And their location. Okay, moving on from there. So this is wrong. The next one is the shape of a molecule is determined only by repulsions amongst non-bonding electron groups. No, it's both the bonding electron groups and the non-bonding electron groups. Even though in assigning the name, we ignore the non-bonding electron groups, right, in assigning the name. But we recognize the effect of both bonding and non-bonding groups. Okay, the shape of the molecule is determined by the polarity of its bonds. Wait, what? No, not polarity. So if all of these are wrong, that makes the last one right? The shape of the molecule is determined by repulsions amongst all electron groups, bonding and non-bonding, on the central atom or interior atom, if there is more than one, okay? So this is the correct answer right here, D. So we care about both bonded and non-bonded groups, okay? Okay, using Vesper to predict molecular geometry. Of course, first you're gonna draw a Lewis structure, determine the number of electron groups around the central atom, classify each electron group as either bonding or lone pair. You want to go ahead and count multiples. If the bonds are grouped together, they're counted as a group. The emphasis there is a group. And then use the big table that we designed, right, to pretty much figure out what the electron pair geometry is, the molecular geometry, aka the shape, and the bond angle and the molecular type. Okay. So here, I'm not going to draw the Lewis structure. That would take a long time. I'm trying to finish this video as fast as possible. So let's assume we've drawn the Lewis structure, right? PCl3. And we're being asked, what is the geometry, aka the shape? So we have 4 groups. This is 1, 2, 3, 4. We have 4 groups, and then out of the 4 groups, we have 1 lone pair. So these are the number of groups. We have 4 groups, 1 lone pair, and then 3 bonded pairs. Oops, let me write it here. Yeah, 1 lone pair, 3 bonded pairs. Based on that, if they ask us for the electron pair geometry, this would be tetrahedral, right? Because we have 4 groups. But since one of the groups is a lone pair and not a bond, this is molecular pair geometry. This will be trigonal pyramidal, okay? So remember I told you guys this is a chicken foot like that? It would be like if you didn't call this a chicken foot, or if it was a chicken foot, it would be a broken chicken foot, right? So you take the leg part off and all you have left is the bottom part, because up here is where you have the lone pair. And the lone pair shape doesn't count towards the actual geometry. Okay. Okay, so you refer to this part right here and then you figure out what's going on because they have to show you all of this. So remember when you're reading the group of 4 or the 4 electron groups, you have 3 options to pick from, right? 3 available. Our configuration in our picture fits this part here where we have 4 electron groups total, 3 bonded groups, 1 lone pair. Okay, so next one I want to work on is this one here. So even though we have the answer provided, I want to go ahead and work this out. Let me see if I can get a piece of paper here, add a page. So we are working on ICL4, right? ICL4. Is it minus or is it plus? Okay. So based on this, we have a central atom, I. We have 1 I, and I is in group 7, right? So I is bringing in 7 electrons. We have chlorine. Chlorine, we have 4 chlorines, each bringing in 7 electrons. 4 times 7 is what, 28? And we have the extra electron, and we'll say this is 1. This is the extra electron I'm referring to. Of course, you have I right here. So I'm going through and figuring out my total valence electrons, okay, which is key for drawing our Lewis structure. We have to draw the Lewis structure before we can decide what the geometry is and what the bond angle is between the bonds. Okay, even though they have it done, I'm going to go through this real quick and then get our structure squared away. Okay, so we essentially have 28 plus 8, so we get 6 and then 30. So we're working at 36 electrons, right? Our central atom is I, surrounded by 4 Cl, 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 Cl. From here, I'm going to draw 4 bonds, each using up 2 electrons, so we're subtracting 8 electrons, so we are left with 28, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 times 4 is 24. We're left with 4. 1, 2, 3, 4. Minus 4, we're left with 0. Okay. Since I used up an extra electron to draw the Lewis structure, I have to put brackets around it according to the rules and put a negative here. Okay. How many electron groups do I have? Well, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. So I have 6 groups. So we're looking at 6 total groups. These are groups. Of those groups, we have lone pair, 2 groups, bonded pairs, 4 groups, okay? So this looks like a square planar. Square planar, based on the chart, right? And the 6 groups, the bond angle here is going to be 90 degrees. Is that what they asked for? Bond angles. So let me go ahead and see what they do. They go to the chart. They said 6 groups, right? So you have to go all the way down to 6 groups, all the way down to 6 groups. And our options are 3 to pick from. We have 6 groups where all 6 groups are bonded groups. That's not our case. 6 groups where 5 groups are bonded groups. That's not our case. 6 groups where 4 groups are bonded groups. That is our case. Right? That's what we're dealing with. Bond angle, 90 degrees, shape or molecular geometry. This is the same thing as the shape. This is square planar. Okay? Okay, I hope once again that as I'm showing you guys, this is kind of straightforward. Okay, the next thing I want to talk about real quick here is how to draw 3D representation on a 2D paper. Okay, because chemists, there are challenges that chemists face. The molecules in real life are mostly 3D, not 2D. So how do you illustrate 3D without being a great artist, right? I told you all how in my youth I thought I was a great artist and I learned I wasn't. Okay, the first molecule we encountered that's 3D is actually tetrahedral. This molecule here is 3D. So what we do is, they said that how to draw 3D. By convention, the central atom is put on the plane of the paper. So the central atom is in the same plane as the paper. And then you put as many atoms as possible in the same plane. In this case, the straight line here will indicate the same plane as paper. Okay, let's make a central atom A. And then you have up and left. These surrounding atoms are in the same plane as the paper, as in they're flat and flush. They're flush according to the paper or my iPad or the screen. And then you have a bond coming towards you. So the way I rationalized it when I was a student, because I do have astigmatism, and with astigmatism, especially when my eyes are very strained, it's hard for me to see people's faces to really distinguish them from far. It looks blurry because everything looks blurry to me. Words look blurry, a lot of things look blurry. And so I thought to myself, hey, let me use that condition to my benefit. So when the wedge is pointing towards you, it looks more solid because it's more clear. So this is a wedge pointing towards you, away from the screen, towards you. Remember, this is 3D. And then when it's going far away from you, then it looks like, the astigmatism effect, to where it's kind of blurry. So this is like a blur right here. Okay. So you have lying in the same plane as the paper or the screen, towards you and away from you. And this is essentially 3D in the world of chemistry. So you have the straight line in the same plane as the paper. You have wedge going away from you, the blurry effect, and then you have solid towards you. Okay, so linear is flat. We don't call linear planar because it's kind of implied. Trigonal, though, we have to specify that it's planar, meaning it's flat. Bent, we don't call bent planar, but we know it's flat because there's no wedge or hatch. The first one that's ever 3D is tetrahedral. You see it's 3D right here, right? Based on the way the bonds look. Trigonal pyramidal is a derivative of that because you have a lone pair up here. So this is it still retains a 3D effect. When it becomes bent, it goes back to being like that. Then we have trigonal bipyramidal, also 3D. Okay. Seesaw, also 3D. When we have a T-shape goes back to being just flat. Octahedral, 3D. Sorry, T-shape is just going to be planar, right? T-shaped. And of course, the linear will be back here, right? And then square planar is in the name. This is going to be flat, not flat. Yeah, this is going to be flat. Oh, no. Yo, hold on a second. I have a call. Let me pause this. Hold on a second. Okay, so we are finishing up this chapter with talking about a case where you have multiple central atoms. How do you deal with that? Okay. So in this case here, remember that chemistry 1411 is the prerequisite for organic chemistry. In organic chemistry, the molecules are much larger and they have multiple central atoms. So how do you deal with them? For the most part, you're going to be encountering that in this class before you get to organic chemistry, right? The authors are compassionate in understanding that you haven't taken organic chemistry yet, even though this is a prerequisite to that class. Most of the time, they'll write the molecules in such a way that you recognize there's more than one central atom. Here's the thing. When you usually have carbon in a molecule, carbon is usually a central atom because it has great bonding power and it tends to be a central atom for the most part, not all the time, right? In this scenario here, we have more than one central atom. So it's actually let me move this one here out of the way. How do I move this out of the way? Okay, here. It's actually an amino acid called glycine. And we have, they might give this to you as NH2, CH2, COOH, okay? How do you know this is actually a molecule that has many central atoms? First of all, the way this is written, right? It looks here like nitrogen is a central atom surrounded by two hydrogens, and then you have, like, I'm trying to draw this structure so you can see the different parts within the structure, the parts within the whole. This is a part, this is a part right here. And sometimes this is even a part, okay? It takes a little bit of practice to get an idea what the part is, but you have a central atom here surrounded by two H's, and of course there are other bonds, but the more obvious ones are the two H's that we see. Here we have a central atom here surrounded by the O, and then you have a central atom here, okay? So when we're trying to draw this out here, as you can see, let me go ahead and see if I can add a page here so we can see how we can draw this from scratch and then move on from there, right? Because for some of you, we're going to have a H1 lab. When you're doing H1 lab on campus, it does require you to do things step by step. And you're given a situation where you have many central atoms, and you have to figure out how to distribute the electrons. Okay, so let me see. I have NH2, so NH2, CH2, and then COOH. So I told you that essentially we have, this is one part, this is another part, and sometimes this is a part also. Okay. So that being the case, you have a nitrogen surrounded by two hydrogens. That takes care of the first part. You have a carbon surrounded by two hydrogens. That takes care of the second part. You have a carbon surrounded by oxygen. Then you have an oxygen surrounded by hydrogen. And it looks something like this. Okay. So when it comes to the total valence electrons, the valence electrons, I'm trying to figure out what the total is. Total valence electrons. Okay, we're starting with nitrogen. We have one nitrogen worth 5 electrons. It's in group 5, so each nitrogen is bringing in 5 electrons. We have 1, 2, 3, 4, 5. We have 5 hydrogens bringing in 1 electron each, so we have 5 and 5. And then we have 2 carbons bringing in 4 electrons each, so we're working with 8. And then we have 2 oxygens bringing in 6 electrons each. Remember, because these are essentially the group numbers, right? So we've got 12 here. So these two make 20. So we got 30 electrons to work with, okay? So going back to the rules we learned before, we form a single bond between the central atom and the surrounding atom. Each time I do that, I'm using up 2 electrons. So I've got 1, 2, 3, 4, 5, 6, right? Connect all the central atoms. 7, 8, 9. So 9 times 2 makes what? 18. Then I'm left with 12. So with the 12, essentially I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Did I do this right? I got 10 here and I got, I'm getting a lot of buzzing on my phone. It's a little distracting. So I think I did it right. I got 30, right? So I got 1, 2, 3. Oh, yeah. I forgot, yo. I forgot. I have a lone pair here. I'm right. Okay. I got 12. Okay, I'm out. It's all the buzzing. Okay. I get easily distracted. So yeah, now nitrogen has octet. Okay. Everything is good. It's got 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Carbon has octet. This carbon here does not have octet. So to help it have octet, we take the lone pairs from up here and form a double bond right there, right? So now it has octet. So this is now good. This is now good. Each of the oxygens are good. So that's your Lewis structure right there. The next thing they're asking for is geometry around the central atoms. So we have 4 central atoms here, right? So what is the geometry? Let me try to, wait, can I highlight these? Okay, so I have this central atom here, and we're gonna call this, we have 4 surrounding groups, right? 1, 2, 3, 4. And so the 4 surrounding groups, one of them is a lone pair that will be trigonal pyramidal. Essentially, you have this, okay? And then this one here, you have 1, 2, 3, 4 surrounding groups where all 4 groups are bonded groups. You have tetrahedral, okay? Then here we have 1, 2, 3, 3 surrounding groups look more like a Y. We have trigonal planar. And then here we have 4 surrounding groups, right? Looks like a V with your lone pair like that. We have bent, okay? So the question here is, how do you, if you are asked to sketch this, like say you're doing H1 lab and you're asked to sketch this, how do you do that? Since we have 4 central groups, one thing I learned real quick, since I'm an artist, no, I'm not. I can't tell you how much I'm not an artist at all. I learned early on to do a zigzag because the central atoms appear to be connected in a zigzag fashion. So go down, up, down, up, down, up. And we have how many central atoms, right? 1, 2, 3, 4. So you're going to need 5 points. 1, 2, 3, 4, 5. Wait, 1, 2, 3, 4. Sorry, we're going to need 6 points. So we got enough. Okay. So we got NCCO. So we have NCCO. Here you have an H. And you have an H right here. And you have the lone pair. And then here you have 1, 2, and H. That makes, so here you can see how you have the trigonal pyramidal. And here you have the tetrahedral. And over here we have double bond O. That makes essentially planar. So you see it looks more Y right here. Here it looks more tetrahedrally. Here it looks more like trigonal pyramidal. And then here this looks more bent. Okay? And that's essentially the structure. I know it's not the best, right? I guess if you wanted here, you could make this one of these a wedge, make one of these dash like that, make one of these a wedge, and then make one of these dash like that. I just feel like it becomes very complicated, but you can do that, okay? Because this is how they drew it. You can see trigonal pyramidal, tetrahedral, trigonal planar, and bent. You will do the same thing with this one here. Tetrahedral, 4 groups, 4 bonded groups, and then bent. Tetrahedral, bent. Okay? The next part I want to talk about that's almost the end is the polarity. So we're told that we looked at polarity of bonds before. Go ahead and look at that lecture. Now we're looking at polarity of a molecule. Just because the bond is polar doesn't mean the molecule is also polar. But we're told here for a molecule to be polar, it must have the following. Number 1, it must at least have polar bonds. And they remind you, remember what polar bonds are? Polar bonds are due to electronegativity differences. The electronegativity of the element gives it access to the shared electrons. It's kind of like a privilege, right? With that, it gets access to the shared electron, and the value of electronegativity is higher. Bond dipole moments can be measured, and the bond polarity creates a symmetry. Okay, so if you have polar bonds, if you have asymmetry in the shape, this can cause polarity. Okay, what else? Why are we learning about polarity? Is it because it's in the lesson plan? I mean, there's that. Yeah, that's the obvious part. But we're learning this because later on, we're seeing that the behavior, remember, we wanted to know why molecules do what they do. The behavior of molecules can be tied down. Some behaviors, not all, some behaviors such as boiling point, solubility, freezing point, the way molecules interact with each other can be tied down to the polarity. And so we're told polarity affects intermolecular forces of attraction. The way one molecule is able to attract the other and bond with it boils down to the polarity of that molecule. So if it has that polarity factor, it will influence how molecules interact with each other, how they form solutions, like dissolves like. When their polarities are similar, they're easily able to form a solution. So we're told, bottom line, in the mechanism, non-bonding pairs will affect the molecule polarity. Okay. Because there's a strong pull in their direction. So what I'm going to do is this. Let's start with simple molecules. The simple molecules like oxygen, O2, nitrogen, N2, right? I'm not going to go through the whole process of drawing the Lewis structure, but let me start with the simple molecules. I'm going to go off script here. And in doing so, I'm going to make this chapter unnecessarily longer, but we have to cover this. So let's start with polarity of the simple molecules. Okay. Usually you have to have a lack of symmetry. So if you have unsymmetrical shape, if you have an unsymmetrical shape, then most likely you have polarity, right? So I want to define the term polarity. I talked about this before, but I want to bring it up again because I want you guys to learn the terminology, right? In this case here, we'll talk about polar to mean different. So when we're saying, let's call it different. When we're saying a molecule is polar, we're saying there's something in the molecule that is significantly different for us to recognize it as polar. When we're saying a molecule is nonpolar, there's something about it that's not different enough. So nonpolar will be none different. Is this proper English? No, it's not. Can you repeat this in the streets of chemistry? Please don't. Keep it in your heart. Non-polar, okay? Non-polar indicating that whatever difference you're observing is not significant enough for it to play a factor in the behavior of the molecule. Okay, so let's start with this. When you have two oxygens bonded together, two nitrogens bonded together, two of the same element, essentially, the Brinkerhoff elements, they tend to be nonpolar. Our judgment here is nonpolar. Why are they nonpolar? Because in the formation of the bond between the two oxygen, whatever ability the one oxygen has, the other oxygen can match it. So we have a tie between the elements. There's no difference between the elements because they're pretty much the same element twice, right? So we judge this as non-polar. Same thing with if you had two fluorines. Yes, fluorine tends to be the element with the highest electronegativity. Two fluorines will still form a non-polar molecule. Why? Because when they're trying to form a bond, they're equally matched. Whatever electronegativity the one fluorine brings, the 4.0, the other one brings 4.0. So what do we have? A draw. There is no difference here. But if you switch it up, right, and bring in, say, a hydrogen and a fluorine, now you have switched things up. By doing that, the hydrogen has a different ability, a different electronegativity, and the fluorine does too. So in this case here, I think the hydrogen is 2.1. I'm kind of whispering this. I don't even know why, because I don't remember it for sure. I think it's 2.1. Fluorine is 4.0. The gap in this here is significant enough to make this bond polar, but we're not looking at the polar bond here. We're looking at the molecule as a whole. So I am not going to use the numbers here. I'm going to use the properties here that make this whole molecule polar. You want to locate the central atom. So our central atom, for the sake of this conversation, is fluorine, right? This is our central atom. So I'm highlighting that here. Let me highlight this. And then you want to look at the electron groups around it, okay? Electron groups. We have this one here, we have this one here, we have this one here, and we have these. We have 4 electron groups. And ask yourself, do you see a difference? Do you see a significant difference in the surrounding groups? Yes. One is a bond. The other 3 are lone pairs. And in the world of judging polarity, these are not the same. They're different. So by the virtue of the lone pair alone, this molecule here is polar because the surrounding groups do not match. One of them is not like the other. Okay. So I don't know. I like to say to myself, one of these things is not like the other. One of these things just doesn't belong. No, don't go to the whole song. Y'all get what I'm saying, right? One of these things is not like the other, doesn't match. So yeah, this is going to be a polar molecule. The other way to make this polar is, once again, you can switch out one of these elements here and make it polar. Let's start with tetrahedral. Tetrahedral right here, we'll start with CH4. CH4 is, this right here is nonpolar. How can I decide quickly this nonpolar? There is no difference in the surrounding groups. The surrounding groups here, they're all single bonds. They're exactly the same. They're all bonded groups, so they're the same. The surrounding elements are also the same. So what I'm looking at here is, number 1, surrounding groups and then number 2, surrounding elements. And I'm trying to see if one of these is different or both are different, then we have polar. If they're exactly the same, when I say groups here, I mean electron groups. Okay, so I can take this from nonpolar to polar by switching a couple of things. Let me try to switch it up a little bit, make this a little bit. Oh no, what did I just do? What did I just do? Wait, what did I do? I feel like I don't know what I'm pressing. What am I pressing? Oh, it's the end. Wait, no, it's not the end. It's something I'm pressing that's bringing. Okay, anyway. Let me switch this up and put a different element here. I'll put Cl. By me bringing a different element here, I've brought in a difference. The difference makes this polar. Okay? And if I change all of these to C, to Cl, 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 I've made it nonpolar again because they all match, right? But if I mix it up and I do half Cl, half H, we're back to polar because some are different from the other. Does that make sense? Okay, so of course this is going to be polar right here. Polar. When you look at carbon dioxide, this is a Lewis structure right here, carbon dioxide. Central atom, once again, is carbon. What is surrounding it? This is almost symmetry. It's not almost, it's symmetrical. We have bonded group here, right? And they look exactly alike. We have surrounding group here, surrounding element here. They're exactly alike. So this is definitely nonpolar. This is the poster child of nonpolar. No different. But if I switch one of these out and I make it say O double bond C double bond S, I just made this polar. Okay, I need to mention something back here. Since this class is the preparation for organic chemistry, we mentioned before that carbon-carbon bonds are nonpolar, right? I love this new feature and I hate it all at once. Oh, because if I lift my pencil, my Apple Pencil just a little bit, it starts writing. And if I reach the edge of the paper, it changes from an eraser to a pencil, to a pen. And I don't always know if I'm close to the edge. Okay, right here. So carbon-carbon bonds, whether single, double, or triple, these are non-polar. Okay, so are carbon-hydrogen bonds. These are all non-polar. So it is possible to have a carbon-hydrogen bond or part of a molecule that is very, very long. And we will call that the nonpolar region because that's the area where you have all these nonpolar bonds. For those of you biology people, when you have a fatty acid, this is the fatty part. So this right here is fatty, okay? Fatty acid. Well, in that case, when you have an acid, you usually have one of these groups right here. But the point here is this will be the fatty part or the nonpolar part, the nonpolar tail. I don't want to get into too much biochemistry or biology part here, but this is usually the nonpolar end. Nonpolar. Why? Because all these bonds tend to be nonpolar. And the polar end will be this part here. This is the polar. Why? Because the surrounding groups, you can tell they're definitely different, right? And so here we're being asked, is NH3 polar or nonpolar? Okay, you can tell our central atom is N, is surrounded by 3 groups that are bonded groups, these ones right here, and then 1 lone pair. So definitely this is going to be polar. How can I make this nonpolar? By making all of the groups pretty much the same. This part, the interior will be physically nonpolar, but you get the idea here, right? When you have a different group right here, oh, I'm struggling with this. It's going to be nonpolar. Okay, so I think I'm done with this chapter. Yeah, I'm done with this. So hopefully this one worked out well, okay? This is the end of chapter 5.